Hi, my name is Emma Button, and this is a presentation of my project entitled Mapping Vulnerability to Heat in the Twin Cities. Our purpose, based off the goals of Catholic Charities and the Department of Environmental Health, two organizations that we worked with for this project, was to identify the communities within the Twin Cities 7-county metro area that are most vulnerable to the mortality and morbidity effects caused by increased summer temperatures. We used ArcGIS to create a map of vulnerability in the Twin Cities. We defined vulnerability as those most likely to experience heat-related health problems in the event of increased temperatures. We used 3 different components of vulnerability to inform this map: demographic, such as socioeconomic status, age, or race; the urban heat island effect; and access to emergency services, which we defined as distance to hospitals or fire stations. Previous research has shown all of these components to be major contributors to increased vulnerability to increased temperatures. The bottom line of our project was which communities will be least adaptable to increased temperatures. As our society continues to develop, there is an increased urgency to understand and predict the relationship between heat and health. Research has shown that recent trends in our society, an aging population, hotter summers due to climate change, increased urbanization, and as a result, greater energy use, all contribute to exacerbate the health risks associated with heat. The Intergovernmental Panel on Climate Change predicts that the frequency or intensity of heat waves, and thus heat-related morbidity and mortality, will increase as global temperatures continue to rise. Increased temperature cause mortality by provoking heat strokes and aggravating existing health issues. Increased temperatures contribute to morbidity by impairing human functioning and productivity, as we have all personally experienced. For this study, we partnered with Catholic Charities and the Ramsey County Department of Environmental Health, both of whom were interested in data specifically for the 7-county metro area surrounding Minneapolis and St. Paul. This map shows the areas considered in our map. Our research question for this project was, given certain established vulnerability factors, namely community demographics, urban heat island effects, and distance to emergency services, which communities qualify as being at the greatest risk? Based on recommendations from Catholic Charities, as well as previous research, we used data from the 2010 Census Bureau to determine the indicators of demographic vulnerability. This is a visual representation of how we used our data to create the map for demographic vulnerability. From the census data, we pulled out the 7 different categories we considered to be indicators of vulnerability. We first converted these from a shapefile to a raster. Once these were converted to a raster, we had to standardize them so that all the values were on the same scale. Some of our categories were originally in percentages, such as the percent of people who had not finished high school, while some were originally in raw numbers, such as median age. We reclassified them all to be on a scale of 1 to 100. We then used the raster calculator tool to create an equation based off of these categories. This is the ArcGIS map showing the spectrum of vulnerability within the Twin Cities. The areas shaded in green are areas of low demographic vulnerability, whereas the areas shaded in purple have very high demographic vulnerability. Most areas of high demographic vulnerability are concentrated within Minneapolis and St. Paul, while very few highly vulnerable communities exist in the suburbs. The next component of our map is the urban heat island, and the urban heat island effect refers to the trend of cities having higher temperatures than the surrounding rural areas. The graph shows this effect by comparing nighttime temperatures of an urban area with that of a rural area. This difference is attributed to 3 main factors, which we incorporated into our map. These are the urban materials used in cities, the lack of biomass, and the geographic landscape within a city. The buildings that make up cities are usually constructed with dark materials that absorb instead of reflect heat. Metal, another significant component of most buildings, has a very high absorbance value, meaning that it absorbs and emits heat more than it reflects it. These types of buildings, along with a high concentration of pavement, are together considered impervious surfaces. This is the map produced using data for impervious surfaces. The darker the shading, the more impervious surfaces are present in that area. We used areas with high impervious surfaces in our final heat island effect map. Cities tend to have less trees and greenery, which means that less shade is available as a respite from heat, and that there's also less evapotranspiration occurring. Evapotranspiration refers to plants losing water from their leaves, which tends to cool down the surrounding areas. This map shows the presence of biomass within the 7-county metro area. The darker green the shading, the more biomass is present in that area. The criteria we used for our final heat island effect map was that there was little biomass present in the communities. We also considered whether communities have lakes or not, because lakes tend to moderate temperatures of the surrounding areas and also generate winds that cool down temperatures. This map shows the location of lakes within the study area. We used areas without a lake present in the final calculation of our map. This is how we constructed our model for the urban heat island effect. We used the raster calculator tool to add together the communities that have no lakes, a low biomass value, and a high impervious surface value. We weighted the impervious surfaces twice because evidence has shown that this has the greatest effect in the urban heat island effect. This is the final map for the urban heat island effect in the Twin Cities. The areas in blue are considered to have low vulnerability, while the areas in red have high vulnerability. Again, there is a trend of high vulnerability concentrated within the Twin Cities, while low vulnerability typically occurs in the suburbs. The final component of our map is access to emergency services, namely hospitals and fire departments. Using the presence of physical barriers, such as buildings and lakes, as well as distance, we calculated how much it costs to get to an emergency service. This cost value reveals a community's ability to respond to change. This first map shows the location of all emergency services in the study area. Fire departments are the red circles, while hospitals are the blue squares. When we added together the location of emergency services, as well as the presence of physical barriers, we were able to use the cost distance tool to calculate the cost of traveling from one point to another anywhere in the cities. The resulting value is known as the friction of distance. This map displays the spectrum of friction of distance in the study area. The areas in darker red have a higher friction, meaning that they have a greater cost or it's harder to travel through them. This is the model we used to calculate the final cost of distance. We added together emergency services and the friction of distance to these services to get the cost distance to emergency services. Our final map shows the cost distance to emergency services. The map is showing how hard it is for someone in any given area to access an emergency service. Areas shaded in dark blue have the least accessibility, while areas in yellow are the most accessible. So to sum it all up, our final vulnerability model brought together the 3 maps we made: high demographic vulnerability, high urban heat island effect, and high cost distance to emergency services. And this is our final vulnerability map. This map represents the communities that, given the 3 factors we considered, are at the highest risk of heat-related health issues. The darker red, the more vulnerable, while the darker blue, the less vulnerable. Again, this map reveals a trend that highly vulnerable communities tend to be clustered around the cities, while the suburbs tend to have less vulnerable communities. The conclusions we drew is that there are communities within the Twin Cities 7-county metro area who are especially vulnerable to heat-related morbidity and mortality. These communities should take priority when considering public health programs or policies. For future research, depending on one's definition of vulnerability, the communities to target could change. Our definition of vulnerability was based on recommendations from Catholic Charities. However, depending on the communities of interest, this definition could change. Here are the references used for the study, as well as the data sources used to inform our model. Thanks for listening.